Hey everyone, welcome to Venus Neuron, your go-to resource for medical school success. Now in this video, we're going to talk about atomic orbitals and electrons and also what are quantum numbers and breaking down everything into simple terms so you would understand them perfectly. Now let's get started. So what are atomic orbitals? They are regions around an atomic nucleus where electrons are most likely to be found. They are defined by mathematical wave functions that describe the probability of an electron's presence in different areas around the nucleus. Each orbital has a specific shape, energy level, and orientation in space. There are four main types of atomic orbitals. I'm sure you probably heard about this, but we have s orbitals, p orbitals, d orbitals, and f orbitals. Now, s orbitals are spherical shape. For example, 1s, 2s, 3s, okay? Or p orbitals are dumbbell shape. For example, 2p, 3p, 4p, and d orbitals are complex and cloverleaf shapes, like 3d, 4d, 5d, not the TD, okay? And f orbitals are even more complex shapes, such as 4f, 5f. Yeah. Now, what are quantum numbers? Quantum numbers define the properties of an electron in an atom and describe its energy, shape, orientation, and spin. So, in another word, it is the explanation of the arrangement of electrons within the atoms. We have four different quantum numbers that will help us to find where it is most likely to find the electrons at a given moment. You can think about these numbers as the electron address. Okay, that makes it more reasonable. Now, before I talk about each of the quantum numbers, I want to talk about quantum theory and tell you what does it say. So quantum theory says that matter and energy have the same property as both particles and waves. So tiny units of electromagnetic energy. Electrons as matter have resting mass and electrical charge, and as energy have no resting mass. The electron cloud of an atom can be best described as a standing wave or like energy. And this 3D wave has different nodes, meaning minimum amplitude. It has shape, symmetry, and orientation. Okay? Now let's talk about principal quantum number, which is the first quantum number that we're going to talk about. It's shown with a small letter n. It describes the main energy level, or in other words, the shell of the atom. It could be equal to 1, 2, 3, and so on, and it's always a positive number. So based on what I said so far, higher principal quantum number or higher n means higher energy and farther from the nucleus. The next number is azimuthal or angular momentum quantum number. It's also called subsidiary quantum number. It basically describes the shape of the orbital. It is indicated with small letter L. Now, this L is 1 unit less than the principal quantum number. So we say L is equal to n minus 1. So the first value of L is 0. Okay? Now, if L is 0, then it shows the s orbital. Do you remember what shape it had? Correct, spherical. Or if L is equal to 1, it shows p orbital. Or if it's 2, it shows d orbital. And if it's 3, it shows, do you know which orbital? Nice, f orbital. So L starts from 0 to n minus 1. Okay? The third number we're going to talk about is magnetic quantum number. It describes the orientation of the orbital's magnetic momentum in space. So basically, it indicates the orientation of the orbital and which axis the orbital follows, x, y, z, and so on. It's represented by M with a subscript L, okay, which that L is for azimuthal quantum number. The value of magnetic quantum number is from negative L to positive L, including 0. Let me give you an example. For example, for s orbital, we said that L is equal to 0 and n is equal to, correct, 1. Now, for s orbital, the magnetic quantum number will be 0. And well, since it is a sphere, it will only have one orientation, right? Nothing will change if you rotate it or anything. Or another example for the p orbital. The magnetic quantum number will be -1, 0, and +1. Okay? And well, it means that it has 3 orientations. Okay, as you can see in the picture. Now let's talk about the last quantum number, or magnetic spin quantum number. Okay? Or basically spin quantum number. It is represented by M and the subscript S. It represents the spin direction of an electron. It is basically the phase spin of the electron, so it can either be up, which is positive 0.5, or spinning down, or negative 0.5. So guys, this number describes the intrinsic angular momentum or spin of an electron. Unlike the other quantum numbers which define an electron's position in an atom, the spin quantum number refers to the electron's fundamental property. So similar to how a planet rotates on its own axis. And possible values of this number, it could be either positive 0.5 or negative 0.5, which is spinning up or spinning down. Okay? This leads us to learning what is Pauli's exclusion principle. So, this principle says that an orbital can hold as many as 2 electrons, but only if they have opposite spins. So, those 2 electrons, their 4 quantum numbers cannot be equal at the same time, so at least their spin quantum number should be different. And that is called Pauli's exclusion principle. Okay? So, how are atomic orbitals occupied by electrons? We have 4 rules. The first one is the Aufbau rule. It states that electrons fill the lowest energy levels first before filling the higher levels. So, first we go for orbital S, then P, then D, and lastly F. Okay? That's how we fill it. The second rule is Pauli's exclusion principle, which we just talked about it. The third one is Hund's rule, which states that electrons at the same subshell spread out among the subshell's orbitals as much as possible. Now you might wonder, what is a subshell? So a subshell is a group of orbitals within the same principal energy level, or n, that share the same azimuthal quantum number, or L. Each subshell is defined by its shape and is labeled using the letters S, P, D, and F, which correspond to different values of L. So basically, when we say shell, its energy level, and it's defined by N, or principal quantum number. For example, N equals 1, 2, 3, 4, etc. When we say subshell, it's defined by L, or azimuthal quantum number. Possible values are 0, 1, 2, 3, and so far, corresponding to S, P, D, and F subshells. Okay? But when we say orbitals, each subshell contains a set number of orbitals defined by magnetic quantum number. Okay? So, based on what we've learned so far, the s orbital, it's a type of orbital. It has a spherical shape and it has one orbital within it. Okay? Or when we talk about p orbital, it has a dumbbell shape and we have 3 orbitals. Or when we say d orbital, it has a clover leaf shape and has 5 orbitals. Or when we say f orbital, it has a complex shape and has 7 orbitals. Well, let me give you another example. For example, subshell 2p. The shell or energy level for this subshell is 2, so it has second energy level. Its azimuthal quantum number, or L, is p, basically L equal 1. The number of orbitals in the 2p subshell are 3 because the m subscript L, or do you remember what was the name of it? Good job, magnetic quantum number. Its value is -1, 0, and +1. So we have 3 orbitals in the 2p subshell. And the maximum electrons in 2p subshell are 6 electrons. Okay? I hope you understood it so far, and if you haven't or if you have any questions, let me know in the comment section. Now let's keep going. Now, have you heard that in the third layer we have 18 electrons? Do you know how we got to that number? Well, the maximum number of electrons in a given energy level, or n, is determined by this formula. It's equal to 2 multiplied by n raised to the power of 2. So for the third layer or third energy level, or n equals 3, the maximum electrons will be 18. Okay? So let's go into a little more detail. Why 18? So the third energy level consists of 3 subshells. The s orbital, which has 1 orbital and 2 electrons. The 3p, or 3p subshell, you can say it that way too. 3p subshell, which has 3 orbitals and 6 electrons. In 3d, we have 5 orbitals and 10 electrons. You know that in each orbital we have 2 electrons, right? Okay, so adding these up, we have 18 electrons. Okay, now you might wonder, why don't we have an f orbital in the third layer? So the f orbital, or L equals 3, only appears when n is bigger than 4, equal or greater than 4. It means 4f, 5f, and etc. Since L ranges from 0 to n minus 1, so L equal 3 is not possible for n equal 3. Okay? Moving back to the last rule that we want to talk about, which is Madelung's rule. It states that orbitals fill with electrons in order of increasing n plus L value, so the sum of the principal and subsidiary quantum numbers. Okay, look at this. You can see that first we have 1s, 2s, 2p, 3s, 3p. You might expect that the next orbital to be filled be like 3d, but interestingly it's 4s that fills first, okay? It's because of these values that you can see here. That's why I think now you understand the exceptions in the periodic table. And guys, that was all for today's video. In the next video, we're going to talk about different types of primary bonds and go through every single detail for it for you to understand it better. And as I always say, stay curious, keep learning, and I'll see you in the next video.